Visual Graph Query Interfaces, referred to as VQI, facilitate non-programmers to query graph data effortlessly. Construction of these visual interfaces for large networks is typically not data-driven. That is, it does not exploit the underlying networks to automatically generate the contents of various panels in a VQI, such as the toolbar panel, the label panel, default patterns panel and query construction panel. A useful component in a VQI that can facilitate both top-down and bottom-up search is a panel containing a set of small subgraphs or patterns. Specifically, a pattern enables a user to construct multiple nodes and edges in a subgraph query by performing a single click and drag action, referred to as pattern at a time mode, in lieu of iterative construction of edges one at a time. In bottom-up construction, there is no clear pattern in mind and these patterns act as representative objects to kickstart query formulation. Simply having a VQI with only default patterns or no patterns is challenging for visual querying since large networks tend to resemble a hairball, making them hard to browse. Furthermore, default patterns such as triangle and two paths occur in all large networks. Hence, these default patterns are not informative with regards to the topology that is characteristic of the underlying network. As such, they are of little use as representative objects to begin search in bottom-up mode. In this video, we demonstrate a novel data-driven visual plug-and-play subgraph query interface construction system called PLAYPEN. Given an input which is a large graph such as Amazon dataset, PLAYPEN automatically populates various panels of the VQI from it. A key feature of PLAYPEN is its ability to generate patterns which the user can browse for formulating queries. PLAYPEN preferentially selects patterns with low cognitive load, but of high coverage of the graph and achieving high diversity as a pattern set to improve its usability for query formulation. Hence the canned patterns go beyond the default patterns that tend to occur in all graphs. As such, they serve as better representative objects for both bottom-up and top-down searches. We shall now demonstrate the bottom-up search paradigm on Amazon dataset. First, we select the Amazon dataset. Then, we configure the plug properties consisting of the number of patterns in the set and their minimum and maximum sizes. In this dataset, the labels represent actors and movies. The generated patterns can be easily browsed and interpreted due to PLAYPEN selection of patterns with lower cognitive load. Suppose the user would like to find out more about co-actors of Ben Affleck and Matt Damon but is unsure of how to start his search. He can browse the generated patterns. The patterns containing diamond shapes trigger his thoughts as he recalled having watched Good Will Hunting and Glory Days that both features the two actors. He then decides to pick one of these patterns to start his bottom-up query construction. He starts by assigning nodes in the diamond shape with labels for Ben Affleck, Matt Damon, Glory Days, and Good Will Hunting. Then, he decided to expand his query to also examine movies of Kate Winslet and Gwyneth Paltrow who acted in Contagion together with Matt Damon. To facilitate construction of this query, he assigned the node with label for Contagion. Remove a node and an edge. Assigned another node with label for Gwyneth Paltrow. Finally, he added a new node and a new edge and then assigned the new node with label Kate Winslet. We now demonstrate PLAYPEN on the DBLP dataset, which is a co-authorship network where two authors are connected if they publish at least one paper together. PLAYPEN allows user to easily switch between dataset. Since a user may have different usage for a dataset, plug properties can be easily configured according to needs. In this example, we will show top-down query construction of the co-author network of Peter Carney and David Hickey. Unlike the previous example, in this example, user have a clear idea of the query subgraph he is interested in. First, we demonstrate query construction using generated patterns. The user selects a chord-like pattern and drag it to the construction panel. Then an edge is removed. To complete the pattern, he switches to use the two-path pattern in the default patterns panel. Observe that PLAYPEN allows the users to harness all three construction modes, namely, edge at a time, use of default patterns and pattern at a time seamlessly during query construction. Then the nodes are assigned labels of author names. Query construction using generated patterns took 54 seconds. For comparison, we demonstrate the construction of the same query using edge at a time approach. In this approach, repetitive construction of node and edge occurs. A total of 18 steps is required to construct the query subgraph topology using this approach. In comparison, only 4 steps is required using generated patterns. Similar to our earlier query construction, we assign author name labels to each node. Query construction using edge at a time approach took 1 minute and 11 seconds. Hence, the use of generated patterns can help to reduce both the number of steps and the time taken for query construction. In summary, as more and more graph data sources become prevalent in a wide variety of domains, PLAYPEN can help to minimize the cost of development and maintenance of VQIs. We have come to the end of the video. Thank you very much for your attention.